Illustration number 10. An object is allowed to fall freely towards the earth from a distance r which is greater than the radius of the earth from the center. Now we have to find out the speed of the object when it strikes the surface of the earth. Now first of all, when the object is freely falling, then its initial velocity is 0, and according to this initial velocity is equal to 0, the kinetic energy of the body at the time of its freely falling is also 0, but there exists its gravitational potential energy U is equal to minus G me into m divided by r square, and here remember the value of r is greater than the radius of earth. And now when it will strike the surface of earth, so the velocity of an object when it strikes the surface of the earth, and so at this particular time I am consider that the velocity is small v, and hence its kinetic energy K is equal to 1 by 2 mv square. And here at this particular point the potential energy or improper gravitational potential energy is minus G me small m over Re. So this is the first equation, and this is my result number 2. Now if we neglect the air resistance, then the law of conservation of mechanical energy can be given by kinetic energy plus gravitational potential energy at distance r from Earth's surface that is equal to kinetic energy plus potential energy at exactly Earth's surface, not at a distance or not even at a small distance. Therefore, now here the value of kinetic energy is 0 plus the value of potential energy is minus Gme small m over r, that is equal to kinetic energy is 1 by 2 mv square and the potential energy is minus Gme into m divided by Re. With this result, we can find out by simplification GMEM over R. I am taking this term on the left hand side. So it will be plus GMEM over RE is equal to 1 by 2 mv square. Now from the left hand side I can take common G and M, or GMEM. Let me take common. So GMEM inside the bracket 1 over RE minus 1 over R is equal to 1 by 2 mv square, and therefore from the both the sides m is cancelled out. Therefore the equation for v square is equal to twice GME into the bracket 1 over RE minus 1 over R. So this is the third important result. And now, to obtain the answer in terms of G, means we have to find out the gravitational acceleration and it should be related to the velocity v. Then we have to consider G is equal to GME over RE square. And from this equation, the simple value of GME is equal to G into RE square. And therefore, equation 3 has been now modified to twice GRE square inside the bracket 1 over RE minus 1 over R. But this is the equation of v square and our target is to find out the speed only. So taking square root on both the sides. So we will get v is equal to, in the bracket, twice g RE square into the bracket 1 over RE minus 1 over R. The bracket is over and whole raised to 1 by 2. So the equation number 5 is the required result. And you should note here one thing. If it falls from the very long distance, if R tends to infinity, then the velocity v will equal to under root twice GME over RE, or you can consider it as under root twice RE into G, which is same as the escape speed, that is equal to VE. So this is the end of illustration number 10, and now we will study the most important topic for which we have studied the gravitation, that is the satellite. Illustration number 11. Imagine a simple pendulum suspended from a support which is at infinite height from the surface of the earth, and the bob of the pendulum is close to the surface. Now, since the point of suspension is at infinite height, from the surface of the earth, then the small path of motion of the bob can be considered as a linear motion or the linear path. And now I am consider that the mass of the bob is small m. And also, when the bob is released from the height, so let me give you one diagrammatical arrangement. So, when the bob is released from A, then the force or the gravitational force, but in which direction? It is only in the x direction. So I am taking the component of that with the angle theta. So the x component is mg cos theta, and we consider that the Fg value is equal to mass into gravitation, and this force is providing the necessary restoring force at position D. That means the restoring force on the bob F is equal to minus mg cos theta. Because the force is restoring, so the negative sign will come. And from the figure, I can find out the value of cos theta, but before that I am giving this as equation number 1. The value of cos theta is horizontal arm and vertical arm division. So it is X over RE. Here RE is the radius of the earth. But if the bob, it is closed to the surface of the earth, then we can take this distance AO or the distance BO and the distance CO as RE. It is actually the radius of the earth. And here then we have considered the motion or the path of the bob as a linear one. So AO is equal to BO is equal to RE. That is equation number 3. And therefore the value of force F is equal to minus mg, substituting the value of cos theta, x over RE, and it is equal to minus kx, where k is equal to, this is equation number 4, mg over RE is force constant. And this equation indicates that the pendulum performs simple harmonic motion. And from the equation of time period for simple harmonic motion, T is equal to twice pi under root m by k. And now substituting the value of k in this equation, so it is twice pi under root m divided by mg over re. So here m is cancelled. Therefore, time period t is equal to twice pi under root. This denominator of denominator will come into numerator. So it is re over g. So t is equal to twice pi under root re upon g. And this is the equation what we have to determine. Now same type of illustration is illustration number 12. We are going to solve that.